Okay, welcome everyone. This is another Friday CGU talk series event. This week we're going to be focusing on solid earth section talks. So I'm Claire Curry and I'm the president of the solid earth section at the moment. So I have been tasked with introducing the speakers and I'll also be coordinating the question and answer period at the end. So I think everyone who's through Zoom should see a Q&A button at the bottom of the screen. So if during the talk you think of a question, then click on that and you can type your question right into the box that comes up, and then I can convey that to the speakers at the end of the talks. Okay, so hopefully we'll have the speakers talking for about 10 to 12 minutes or so, and then we'll have a period of question and answer, and then a few minutes to change over to the next speaker. Okay, so we've got on deck today 5 speakers who are all present, so that's great. So we're going to kick things off with Omid, who is going to be presenting some of his work. He's a graduate student, I think a PhD student, is that correct? At the University du Quebec à Montréal. So he'll be presenting some of his work on the structure of the lithosphere in Eastern Canada. So I think, Omid, if you're ready, you can share your screen and then off we'll go.
Okay, great. Can everyone hear me? Great, yes. Awesome. I would like to thank the organizers, first of all, for giving us this opportunity to present our work, and I hope everyone continue to stay safe in this pandemic. I'm going to share my screen and host disable attendee screen sharing.
Yep, sorry. You should be able to do it now.
Should I try again?
Yep, you should be able to do it now.
Okay. Okay, can you see my screen now? Okay, great, awesome. So today I'm going to walk you through some results of my PhD project. In my PhD, I tried to achieve highest resolution tomography images of crust and uppermost mantle for easternmost Canada and northeastern USA. The results you will see in my slides today are actually related to the first paper of my project. I'm currently writing the manuscript and it will be hopefully submitted very soon. I have divided my talk into 4 sections. In the first section, I will introduce you to the main problems and objectives and a little bit of a tectonic history of my region. Next, I get you informed about the data set and the method used in this study. And in the third section, you will see some colorful maps and cross sections of the tomography inversions. And finally, I use those results to discuss tectonic implications. So the big problem in my research domain is that as much as we are knowledgeable and informed about the initial formation and evolution of oceanic lithosphere, we know nothing about continental lithosphere. This is because continental lithosphere is much more complex and has many more years of tectonic history. Good news, Eastern Canada is an excellent natural laboratory to address this issue, and because it has experienced a very long tectonic history. So in this study, I use a surface wave tomography technique to obtain highest resolution velocity structure of southeastern Canada and northeast of USA to date, and the depth range is between 50 to 200 kilometers. Here's a simplified tectonic map of Eastern Canada. At the core of North America, we have the Archean Superior Craton that is not included in our study area. Actually, I've marked the study area by the dashed line here in this map. In the Northwest, the Grenville province has over 1 billion years of tectonic history. It is separated from the Northern Appalachians by this red line that is actually a major faulting system called the Appalachian Structure Front. In Northern Appalachians, we have 5 different tectonic zones, and previous authors have divided also these domains in, based on their origin. So the Humber zone is actually peri-Laurentian. Gandaria, Avalonia, and Megoma, they're separated from supercontinent Gondwana, so they are peri-Gondwanan. And Dunwich zone is actually has terrains, a mixture of both. So here's the data before I get you familiar with the method. So I selected 46 earthquakes out of more than 300 in the in time window between 2013 and 2015, based on quality of the events and also the azimuthal distribution. More than 70% of this data were only recorded during this time window in like TA network, the X8, actually the QM3 experiment, and the SeisUK temporary stations. So that's why this time window was chosen for my data set. Here's an example of the processed data. You can see over here, here's the unfiltered data, the vertical component of seismograms, and different bandpass filters. You can, that is actually related to an earthquake that of magnitude 6 that occurred on mid-Atlantic ridge and recorded by a station in Nova Scotia. Not all data is that great visually, and we have rubbish data we have to throw out. After we're done with the processing of the data set, we can plot the Great Circle path maps for each pass bands. And for your information, the average number of crossing ray paths in my study area is 3 times the one that mentioned in the original paper. Okay, the tomography method we use is called two-plane wave tomography that includes important improvements over the traditional approaches. Basically, when an earthquake passes through a tectonic boundary, it gets scattered, and this makes the wave field much more complex than a simple plane wave. So two-plane wave tomography assumes the earthquake wave field is actually consists of 2 plane waves interfering with one another, and by tracking this interference over a study area, we are able to obtain tomography images with higher resolution. This method was also further developed to take finite frequency into account. That is a more accurate representation of the sensitivity of the waves. We need 3 inputs, phase and amplitude data. We can apply Fourier transfer to time series. We need a starting model. I use the continental scale model by Schaeffer and Lebedev 2014. And we also need a grid of nodes that is over here. You can see in the black dots in this cartoon. So here's the results of inverting the data set for an average dispersion curve. Dispersion curve is a curve that is plotted in the phase velocity or group velocity versus period or frequency domain. And that represents the phase velocity variation for the entire study area. To generate the phase velocity maps at each period, we have similar curves at a grid of nodes. So here are the phase velocity maps, the useful output of the tomography program. You can see the phase velocity maps at different periods. The inversion also output the covariance matrix that you can use to do some error analysis. And I used the contour of 1.5% for the map of 2 times the standard error at a 95% confidence interval to mask the area that I statistically can say are like the outputs are reliable. So each phase velocity map show integrated information about velocity structure for a depth range, but has a maximum sensitivity to a particular depth. So you can see the maximum sensitivity of each map that I marked at the lower bottom of each map. So for example, at 30 seconds, the maximum sensitivity is around 39 kilometers, but it has a plus and minus. So in the top panels, you can see I'm showing the phase velocity variation sensitive to lower crust. Middle panel, you're seeing the velocity structure of lithospheric depths, and in the bottom panels, you see velocity variation over lower lithosphere and sublithospheric depths. Red colors, for example, in these crustal depths could indicate thicker crust over Grenville, as you can see. You can still see the systematic variation of crustal thickness. In the middle panels, the blue colors here show probably a thicker lithosphere in Grenville, in New Brunswick, and Nova Scotia. And you can see some consistent low velocity zones over this area that is due to passage of Great Meteor hotspot, and some other low velocity zone over Gulf of St. Lawrence and Gulf of Maine. So here's a famous checkable resolution test that we do after the tomography that certified the high resolving power of our method and data set. Basically, you make an input model like this, and you try to recover the same model by inverting the synthetic data that is generated based on the process data set. And these maps are actually useful to check how well the geometry of features are recovered before giving any interpretation. Because phase velocity gives us information about a depth range, we need to have the velocity information at actual depths. So we invert the data for shear wave velocity structure. We use a program called ShearCyto that is also further developed by Dr. Lee's group in University of Houston, Texas. And the inversion also output the resolution metrics that can be used to identify the depth at which you want to cut your model. We choose the 200-kilometer depth, and we cut the model in this depth range. That was actually a result of inverting 1D average dispersion curve for a 1D average shear wave velocity profile. Here you can see the maps generated from inverting the phase velocity maps at all periods. So in the ShearCyto program that I described you in the previous slide, crustal thickness is also allowed to vary. You can see our recovered crustal thickness model over here. I compared the results to the results from receiver function, the red circles over here, and you can see the method was able to capture the variation. And the values over the top of the maps are actually the reference model from AK135, and we usually plot our maps based on perturbation from a reference model and use a proxy to locate, for example, lithosphere and asthenospheric boundary. So the systematic variation of velocities at different domains are observed. For example, over here, you can see clearly higher velocity values over Grenville, lower velocity over Dispatch. But I would like to draw your attention to one feature over here. And I want to base my discussion over this area, in New Brunswick, the high velocity values over here, to give interpretation about variation of LAB depths. We choose the value of 1.5% as a proxy for locating lithosphere asthenospheric boundary. Here's another view of the same result, the cross-section view, and you can see the variation of lithospheric thickness, for example, in this profile as we go toward the southeast. Here's the interesting feature that I would like to discuss about. In New Brunswick, we have a very thick lithosphere, and I want to provide you some evidence for the reason why that lithosphere there is that thick. So we know that the convergence of Avalonia to North America in late Silurian was associated with the flat slab setting. We have evidence from palomagnetic studies, from isotopic studies, and also from actually from the the most importantly from the bimodal distribution of age of the volcanic rocks. So when two actually continental piece, two pieces, an oceanic piece and a continental piece, one is going to subduct to another one. If the convergence rate is very high, one can go, the oceanic one can subduct very shallow. And that is actually evident in the palomagnetic studies. You can see the high convergence rate in the palomagnetic studies. And that's one evidence. The other one is high values for the ratio between these elements, LA over YB and SR over Y, very high values, and low values for this YB element that is typical for a flat slab setting. For example, you can see the same values for in Chile. And the most importantly, we will see a two-stage magmatism in the flat slab settings, because when one slab subducts to another one, we have a limited magmatism due to bringing the water content. And the next phase of magmatism occurs when the slab breaks off. We see the same evidence for the age of the volcanic rocks. So my conclusion here is that the thick lithosphere over here is associated with the flat slab setting. So some take-home messages. The Grenville province and the Northern Appalachians are great study regions because they have very rich tectonic history. But Northern Appalachian is highly tectonized, and that does not show a simple relation between the age and the LAB depths. As an example, you saw the New Brunswick area, and the latest magmatism that I discussed previously is related to the passage of Great Meteor Hotspot that modified the lithosphere, particularly evident in the Perigondwana domain. And the evidence from flat subduction of Avalonia beneath Gandaria explains the thick lithosphere beneath New Brunswick and Nova Scotia. Thank you.
Thank you very much, Omid. Are there any questions? I don't see any in the Q&A box, but we have a minute or so for questions if there are any. Okay, I'm not seeing any questions at the moment. I did have a quick question for you. You talk about flat subduction as being the reason for the thick lithosphere. So I'm wondering, are you envisioning the flat slab as sticking to the continental plate and that's created the thickening, or is it thickened through compression?
Well, I think even like accretion of megoma, the next train to the south is also played a role, because right after subduction of Avalonia beneath Gandaria, the slab, I think the slab broke off to the east. Then we have the megoma arriving. Then we have another slab breaking off other side. And so it's a combination of processes that I think that contributed to thickening of the lithosphere over that area.
Okay, thank you very much. There's a few questions have arisen. We've only got about a minute for this. So I'll just go with Phil is asking, what are the lateral changes in the crustal structure that you're seeing?
Right. So my method is not actually the most accurate one to capture the variation of crustal thickness, because it's not sensitive to if for example, if the crust mantle boundary is very sharp. But the variation you can see, for example, in this map, can you see the screen? Okay, so you can see, for example, we have a thicker crust over the pre-Laurentian domain. In Gandaria, here we have a shallower crust. Again, in Nova Scotia, the crust is very thick, and here in Gulf of Maine, again, we have a very shallow crust. But if you compare this result with the previous receiver function studies, you can see the method could capture the variation, but not in the actual range. So it couldn't capture the very thick crust. I was just wanted to show you it could capture the variation, but it's not the best method to resolve crustal thickness for sure.
Okay, thank you very much. I'm afraid we're going to have to move on to the next talk. So hopefully the people that have asked questions can get in touch with you about them.
Awesome, thank you.
Okay, thank you. So for the next talk, we will be moving a little bit further west to the Mid-Continental Rift. So Andrew Frederiksen is going to tell us about his work there. So take it away, Andrew.
Just a sec, getting the screen sharing going here. Okay, so yeah, what I want to talk about is the Mid-Continent Rift in Central North America. Hence the title. So I've got a few collaborators on this. I'm showing some student work by a couple of from a couple of honors theses, Parth Pokhar and Barrow, and sort of the larger project and interpretation being developed in collaboration with Justin Revenov, University of Minnesota, and Suzanne Vanderlee of Northwestern. So first of all, here's where we're looking at. If you look in the upper left-hand corner of the map, you can see sort of just a indication of where this is. We are sitting around the Great Lakes, though here I've overlain on that both the magnetic map and the outlines of some major tectonic boundaries. So the Great Lakes region is sort of where a bunch of Proterozoic origins accreted onto the Superior, and were then cut through by a major rift, the Mid-Continent Rift, which is roughly contemporaneous with the youngest of those Proterozoic origins, the Grenville. There's also been some other tectonic events here that could have affected things, like the meteor hotspot tract, which was just mentioned in the previous talk, and you can see how it comes through just right here. And the Superior itself is Archean, obviously, but it has subdivisions within it. I haven't shown all of those belts here, but there's a series of tectonic belts within it. And there's one terrain at the south, which is worth mentioning, the Minnesota River Valley terrain, which is somewhat unusual and is one of the oldest terrains in the Superior. So the Mid-Continent Rift shows up in potential field images, especially in gravity. Here's a gravity map, and you can see that because of the large amount of basaltic volcanism associated with the Mid-Continent Rift, there's a major gravity high that follows the rift axis all along here and outlines the rift's inverted U shape. But it's always been a bit of a puzzle as to how, first of all, why this rift failed, and to what extent it broke through the lithosphere and modified the lithosphere. So from 2011 to 2013, a project was put underway called the Superior Province Rifting Earthscope Experiment, or SPREE, because these kinds of field projects always seem to have an acronym. And this was carefully timed to coincide with the passage of the Earthscope transportable array through this region. So on this map, the gray triangles are the transportable array stations for the most part. There's a few other stations in there, particularly in Canada. And then the SPREE project is shown as black arrows, which was subdivided into sort of 4 subarrays. A sort of more diffuse array north of Lake Superior, which was basically intended to make sure that there was coverage on both sides of the lake at the same time. And then dense arrays along the SM line and across the SN and SS lines, the rift axis itself, where the rift is on land in Minnesota and western Wisconsin. And so the idea was to look at the effect of rifting on both the crust as a whole and the underlying lithosphere. And you can apply with this 2-year passive seismic deployment, you can apply a bunch of different methods, including tomography, receiver functions, and what I'm going to talk about, shear wave splitting. So I don't think I need to, since this is a more geophysical audience, I don't think I need to go too much into the basics of shear wave splitting, but essentially it's a birefringence analysis that takes advantage of the fact that certain teleseismic phases have a known plane polarization, notably the SKS ray path, which emerges from the outer core into the into the mantle with a linear polarization, as you can see here. And if that passes through material that is anisotropic, that is, has a seismic velocity that varies with polarization, then depending on the alignment of the incident polarization with that fabric, you can split that incident wave into a fast and a slow wave that are respectively aligned with the fast and slow directions of the horizontal fabric. And then these will separate and thus split because the faster wave travels faster than the slower wave. We can be reasonably confident that this is all happening above 410 kilometers, that is in the upper mantle, because it's generally attributed to preferential orientation of olivine crystals, and you need olivine to get that. So here is some raw data. It doesn't look that raw, but it kind of is. And that all I've done here is taken the SKS pulse from a single earthquake. This one was in Papua New Guinea, and it's not an accident that I chose this one. It's one of the best splitting earthquakes I've ever seen. And this is just the particle motion. That is the sort of motion of a point on the surface in the horizontal plane that you would see at each of these instruments for the SKS pulse. This shows the polarization of that pulse. And so you can see anything from almost linear polarization here to big fat elliptical loops here, which indicate a stronger splitting effect. The strength of that splitting effect depends on both how strong the fabric is and how the orientations interact. For instance, if your wave is coming in precisely along the fast or slow direction as its incident polarization, it won't split. But what we can mostly see out of this is that because this aspect ratio of this loop is varying so much across this study area, and here we're looking at the dense part of the Spree array, that we expect lots of variation in the splitting parameters. So to get better than this, we actually have to analyze these data. And there's various well-developed methods for doing shear wave splitting analysis. The one that my group uses is a pretty standard one. We look at essentially the initial particle motion, shown as this sort of loop here. You can also look at it as a north, south, and east, west trace, or as a radial and transverse trace, and do a grid search for the possible splitting parameters, that is the orientation of the fast direction and the time separation between the fast and the slow wave. So you assume that it's been split by a simple single layer model, reverse that effect, and see how linear the particle motion you get back is. And that's what's shown down here. So here's nice linear particle motion, which shows up as a low value of the second eigenvalue of the covariance matrix, which is just a measure of motion linearity. And so you can, from that, you can pull off a measurement. And you can use another criterion instead, the energy on the reconstructed transverse component. In this case, they give you basically the same thing. I prefer the eigenvalue measurement because it's more robust in case that you didn't know the incident polarization as well as you thought. But the main point is, if you look at these sort of error surfaces, as they're called, though we can get a single measurement out of this, the robust observable here is in fact the dark colored region, basically the zones of possible parameters that are reasonably compatible with this particular trace. And so instead of interpreting a single event measurement, we want to put together a bunch of these. And so the final measurements we get are composites obtained through a two-stage stacking procedure that tries to directionally balance the results from earthquakes from lots of directions. And then here are the results shown in the traditional way to plot shear wave splitting measurements, which is as double-sided arrows. The arrows are pointing in the direction of the fast wave polarization, and the length of the arrow indicates how strong the splitting is. So how much of a time separation there is between the fast and the slow wave, as average between a large number of events. So the red arrows here are from this study. Black arrows, like these ones here, there's a few here, are from previous study from U of M research group, and let's use this same basic method. The gray arrows are from a study by Ferre et al. From 2014, which used a similar method, not exactly the same, but close enough to be pretty comparable. There's another published study that I'm not showing here because it uses a method that tends to give significantly different results. Now, you can see mostly that these are varying quite a bit. The biggest change is between the northern and southern line. You can see the much longer arrows on the northern line, much shorter arrows on the southern line. And when I originally planned out this analysis, I gave 2 students each a northern and a southern line because I figured, well, those are both going, across strikes, so those are where the interesting stuff is going to happen. But it turns out the interesting variation is mostly happening along strike of the rift, along the SM line, which is basically just an indication of how these things can surprise you. Now, I'm also showing down here, these circles are the width of the Fresnel zone for an SKS pulse for typical frequencies that you'd see at different depths. The point being that you would expect variation due to things happening at 250 kilometers to happen on this kind of length scale, a scale comparable to the diameter of that circle. And so the fact that things are changing over relatively short distances, you can see things like changes in length and changes in orientation that happen over relatively short distances. Those have to be relatively shallow. They have to be near the top of the lithosphere and not the bottom. So here's some results shown as profiles. I don't have a lot to say about these at the moment. These are the fast directions. So they're the orientations. And you can see that they're on the northern line, they're quite consistent. On the sort of north-south-ish line, the SM line, we see some variation, but mostly see a lot more scatter to the south. That's because the more southern measurements, both there's more scatter in the sort of trend of the results, but also the results have bigger error bars. And that's simply because weaker splits are harder to measure, and the split times are smaller in the south. But nonetheless, you can still see there's a definite trend with the MC, note where the mid-continent rift axis is here. You can see that there is a definite rotation of the orientations compared to the flanks of the rifts. I'll come back to that later. If you look at the split time profiles, the pattern is sort of larger scale, and mostly what you see is this south-north variation, with going from very, very weak splits at the southern end of the study area all the way up to some quite strong splits. So for instance, on the SM line, you can see we've got splits of well over a second in places. And if you go down on the southern line, you never really break 0.8 seconds, and most of your measurements are down around half a second or less. So here these are on a map. So if you look at the just the split time, as I've shown here, the main thing you see if you look at the contours is that these contours are cross-cutting the geologic boundaries. What we're seeing here is not something that follows the pattern of the that you see within the crust. Though I do want to point out that the Minnesota River Valley terrain, which I've marked here as MRVT, and that's that sort of unusual terrain I mentioned earlier, has very low split times. That's where we see our absolute lowest values. If you expand this out, include a bunch of previous and some previous work as well. There's a previous study by Ola et al. That looked at the Canadian spree stations and as well as some additional TA stations. Now you can see that the larger pattern is in fact large part due to the edge of a Western Superior feature. That if you get up into the Western Superior, you get very large split times. In fact, this cuts off at 1.8, but if you go further north, you can actually get splits over 2 seconds in places. So there's this tremendous south to north drop in the strength of fabric. You also see some smaller scale features like this weak splitting zone associated with Nipigon embayment. There's another one here that touches basically the end of the Kapuskasing structural zone. And then the new observations, all this stuff here, you can see that the Minnesota River Valley terrain has very weak splits. There's also weak splits continuing further east. But if you look at the fast direction pattern, there we see stuff that seems more related to crustal geology. In particular, I want you to note these two regions here in yellow, which corresponds to about split faster axis of around 90 degrees, which means more roughly east-west, because this is an azimuth, compared to within the rift, you've got something closer to 45, 50 degrees. So northeast, southwest. So there's a significant rotation happening, and you can see it's quite spatially coherent. This isn't just a few stations, and you can see you can follow it up the rift. It's not just showing up on the spree stations, it also shows up in the transportable array stations. There seems to be a zone of altered fabric orientation following the rift axis. So if we throw some zones onto this, we can say that there's a northeast-southwest zone within the rift itself, another northeast-southwest zone in the Western Superior, and then east-west oriented zones in the Minnesota River Valley terrain and in the Yavapai, one of the Proterozoic origins. So what it looks like here is that the rifting has modified the lithosphere. And that's even though it didn't seem to change the split time to any significant degree. So it seems to have reoriented the fabric without really altering its strength. So here's some tomography. This is from a published paper by Bowman et al. 2019. This is a different type of tomography from what you saw in the previous talk. This is body wave based. It's teleseismic travel time tomography using P waves. So in comparison to the surface wave tomography you saw before, it has the benefit of greater lateral resolution. It has much worse vertical resolution, and it's sensitive to relative velocity changes, but not absolute velocity changes. So there's strong and weak points to any tomographic method.
Hi, Andrew, we're just at 15 minutes right now.
Oh, I'm sorry, I'm almost done. I'll wrap this up.
Yep, thanks.
So yeah, in any case, so what main thing to see is that the fast axis contours seem to follow these are the contours, the dashed lines here are the contours from the previous slide, overlaying on this velocity model. And you can see that there is some correspondence, like this low velocity feature here seems to follow the fast axis contours. And this is in the shallow part of the model at 100 kilometers. There seems to be a complex relationship, but there is a relationship. So we're seeing variations in the upper lithosphere. Whereas if you look at the split time, it's not obviously related to the velocity model in a simple way, though it does seem to follow the deeper model a little better, which is why this lower plot is a 200 kilometer slice. So anyhow, I'll skip past this, but this is a receiver function result, and it's just showing that there's an indication of an underplate associated with the rift axis. And so essentially our sort of current interpretation, this is still a little up in the air, I'm still writing up a paper on this, but essentially is that what we're seeing, this rotation of the fast axis may be related to this underplate. So what we'd really like to do is map out that underplate better using receiver functions and see to what extent the stuff that we see is sort of integrated through the whole lithosphere from shear wave splitting and near vertical P waves is in fact can be attributed to a relatively thin layer under the crust. So that's it for me. Thank you very much.
Great, thank you very much, Andrew. We have a question from Cindy Ebinger, who asks, SKS splitting in magnetic rifts are rift parallel with a high % of nulls where the rifts interact with thick cratons. Do you have spatial variations in nulls, and any idea why there's no rift parallel fabric?
Well, for one thing, the mid-continent rift has been reworked. And it may not be, it also may be significantly different from younger rifts. I mean, this is, after all, 1.1 billion years old. But the other thing is the method we're using doesn't really track nulls in that way. So it's a little harder to do that. But at the same time, we are doing purely a single layered interpretation. But what we do look at is how the error surfaces vary in directional swaths. And that would, if there were like strong directional variations incompatible with a single layer model, we would see that. We don't see that here.
Okay, thank you very much. I think we're going to have to move along to the next speaker. So we're now going to change gears and move to convection models on a global scale and looking at how these link with some of the surface tectonic plate boundaries. So we've got Julian Lowman, who's going to tell us about that.
Hi, Claire. Just
Oh.
trying to get this started. Okay, sorry. All right.
Okay, there you go. Okay, here's Julian.
Okay, so I'd like to start by acknowledging my co-authors. That's Sean Langemeyer and Paul Tackley. And the results I'll present are from Sean's PhD thesis studies. Sean set up and post-processed all of these calculations that I'm going to present, and Paul is the principal developer of the mantle convection code that we implemented for all calculations. And I'd also like to acknowledge the support of Compute Canada staff and resources. So motivation for the study is found in a map of the ocean floor age. This one's taken from the work by Muller's group. In particular, I want to emphasize the primary observation we have of mantle convection. The variation in these ages is evidence of the motion at ocean floor and demonstrates a starting point for recognizing what must be obtained from models to be considered to display Earth-like behavior. Mantle convection is expressed by plate tectonics and the generation of a mosaic of broad, low strain rate plate interiors separated by relatively narrow boundaries associated with focused deformation is a primary feature of terrestrial mantle convection. A present-day map suggests further expectations that models consistent with the Earth might exhibit, for example, the number of plates and their mean size. But what we have to keep in mind is that this is just a snapshot of an evolving system. So today we have about a dozen distinct velocity regions comprising the current day number of major plates. We also have some small blocks that may be present along the plate boundaries, and these act like microplates. In this talk, I'd like to focus on the formation of the divergent plate boundaries. This pair of maps depicts bathymetry and gravity gradient data in the Southern Pacific and Atlantic Oceans as determined by Sandwell and Smith. Mid-ocean ridge segments are high elevation linear orange features, for example. These are indicated here by the black arrows. The panels shown also highlight the appearance of offsets, indicated now by the dashed black arrows, and the red and the yellow highlights on the maps. And of course, the offsets are called transform faults, and they follow the term introduced by J. Tuzo Wilson. Wilson's seminal paper on the topic noted that transform faults are strike slip in nature and seismically active only between the offset oceanic ridge segments where divergence is occurring. In fact, divergent boundaries are regularly interrupted by transform fault offsets, and that pattern is globally ubiquitous. These offsets do not appear along convergent plate boundaries. So in this study, we employ the mantle convection model STAG-YY, written and developed by Paul Tackley. The system parameters are G, the gravitational acceleration, D, the depth of the mantle, and RC, the radius of the core. The fluid parameters are alpha, the thermal expansivity, kappa, the thermal diffusivity. We also need a reference viscosity, which we use the surface viscosity, E to surf, and a reference density denoted here as rho naught. And the heating is supplied to our calculations by the core and as well as internal sources that are in the mantle. Boundaries are isothermal, the temperatures marked by a core mantle boundary temperature and a surface temperature that are uniform. I remarked already that we have uniform internal heating, which we've denoted with a chi. And as far as mechanical boundaries go, the boundaries are free slip. I should note that we don't model the cooling of the planet. Accordingly, the core never cools and the radiogenic sources never deplete. So we employ 2D spherical annulus and 3D spherical shell geometries on a yin-yang grid. And the latter calculations feature a resolution of 96 by 768 by 256 by 2. We solve the conservation equations for a Boussinesque infinite Prandtl number flow. And in particular, I want to note that the viscosity is strongly dependent on temperature, mantle depth, and the strain rate. The thermal viscosity contrast in our models is 32 million and is governed by an Arrhenius type of exponential dependence. A yield stress is specified that results in a yield viscosity determined by the second invariant of the strain rate tensor. The yield stress can be depth dependent, as shown in the figure. The figure on the left actually grossly exaggerates the thickness of our two-layer model. The upper layer is generally about 2.5 to 5% of the thickness of the mantle and corresponds to the model lithosphere, where the yield stress can be specified to differ from the deep mantle. We also specify a factor of 30 increase in an intrinsic increase in viscosity corresponding to the lower mantle for the inferred viscosity of bridgemanite in the lower mantle. And the active viscosity in the system is the function shown in this yellow box. If either the yield stress or the thermal viscosity drop by orders of magnitude, then the total viscosity, plummets in accordance. So the 8 calculations that we show here illustrate the effect of the yield stress while holding the other model parameters constant. The ductile yield stress here is increased, but the surface value is held at 0, and the top 5% of the layer is weak. The lower yield stress values result in numerous failure locations at the surface. Higher yield stress values result in episodic failure, for example, in this case marked 1 times 10 to the 8. And then eventually in the highest yield stress cases, 1 times 10 to the 9, we recover a stagnant lid solution for the convection. Now the orange arrow here indicates an example of an intermediate case that features a small number of focus sites of failure and ongoing surface mobility as obtained for a limited range of yield stresses. So this figure shows a snapshot of the interior temperature and the near surface viscosity fields from the initial condition fields used for all the 3D calculations. The yield stress is 0 at the surface and increases linearly to a uniform 2 times 10 to the 7 or 110 megapascals below 2.5% of the mantle depth. The yield stress profile gives a high combination of plateness and surface mobility in the 2D calculations. However, as you can see here, we just find, well, in the 2D, we find 2 or 3 focused downwellings and distinct rigid plates. But in the 3D, we do not find distinct rigid plates as shown in the viscosity field. 3D calculations are integrated forward until reaching a statistically steady state. So we're going to start to vary the yield stress and do exactly that. And this steady state is defined by surface and core mantle boundary mean heat flow agreement within 2% for integration over multiple turnover times once we account for the internal heating. So here we present results from 3 models in which the yield stress is varied while all the other parameters remain fixed. The left column shows the temperature field in the calculation interiors, while the other 3 columns show the viscosity fields at a depth of 12 kilometers. The different columns correspond to different viewing angles. In the top row, we have a yield stress of 11 megapascals at the surface that increases to 110 megapascals at 670 kilometer depth, but we do not get plate-like surface motion. In the middle pair of rows, which come from the same calculation at 2 different times, about 350 million years apart, we use a uniform 110 megapascal yield stress throughout the calculation, and we get something like a plate-like surface. I'll give you more details about this to come. And finally, at 160 megapascal yield stress, specified in the bottom row, we find too few plates. And also we find an odd sectoral distribution in the thermal field and the episodic formation of downwellings. So this figure shows the evolution of the case featured in the second and third row of the previous slide. The period covers about 350 million years. I'd like to highlight a few features here. Some of the behavior in the model evolution shown includes the presence of triple junction migration. This arrow is indicating how a triple junction is moving from east to west, for example. We also find a complete reconfiguration of weak zones or the plate boundaries on timescales of about 100 million years in agreement with the Earth. And there's the formation and growth of strike slip segments along divergent plate boundaries. So to distinguish the nature of the low viscosity boundaries, we calculated the divergence and the radial component of the vorticity field. The convergent boundaries, shown in blue here, do not feature offsets and are smooth and continuous, often extending for thousands of kilometers. But the divergent boundaries, shown in red, form with a structure that is distinct from the convergent boundaries. The divergent boundaries are comprised of spreading segments that are offset by connecting strike-slip features. And this shows up, for example, as these magenta lineations that show up in the vorticity fields. And these can be lengths of tens to hundreds of kilometers. We also calculated the radial heat flux in the vicinity of the spreading boundary, comprised of divergent segments with strike-slip characterized offsets. For example, these white bars are 500 kilometers in length and indicate that the spreading is not entirely symmetric, as well as confirming that the heat flux from the strike-slip segments is much less than the heat flux that's actually coming out of the divergent or ridge-like segments. This figure presents a sequence of slides of the interior thermal field on the left and the near surface divergence field on the right. And this is all at a single time. The different rows correspond to different viewing angles around a common axis. On the left, we show the top, or we have removed the top 100 kilometers of the thermal field in order to view the interior. And on the right, we show the divergence at a depth of 12 kilometers. We find the downwelling sheets sink into the mantle where convergent plate boundaries form, as expected. We also note that there are at least two plumes in the model that reach the base of the lithosphere at this time. We've marked these with an A and a B in this figure. The yellow highlights on this thermal field correspond to divergent plate boundary segments, as we can see on the right. The divergent boundaries in the calculation are passive. So although we find plume-like upwellings that are present in the calculation, they don't underlie the divergent boundaries. We do note that not all the plates are enclosed by focused yield zones at all locations along their peripheries. We observe weakly focused boundaries identified below by a W, diffuse regions of weakness denoted here with a D, and we also find some examples of stronger regions where boundaries might be expected to appear in order to enclose a strong plate interior, and we've labeled those S on the figure. The non-enclosure of all plate-like caps in our models is consistent with terrestrial observations. For example, the boundary running from the Strait of Gibraltar to the Mid-Atlantic Ridge is not sharply defined and may be associated with a nascent subduction zone forming. The region between the Caribbean plate and the Mid-Atlantic Ridge doesn't exhibit any kind of clear weak zone where one has been inferred. And similarly, the meeting of the Australian, the Indian, and the Capricorn plates on the Indian Ocean floor marks a diffuse region. And several other examples exist where plates appear to be largely circumscribed by focused boundaries, but are not entirely enclosed. For example, this map highlights this issue for the Philippine plate and its weakly delineated boundary with the Caroline plate. So I want to make a final note that we didn't model any continental lithosphere, and there's ample evidence that juxtaposition of continental shelves and ocean floor is often a focus for yielding. So that might produce more plates in future calculations. So to summarize what we've found so far, weakening due to convection-induced stress results in transform-like offsets along divergent segments at the surface of spherical shells. Divergent and convergent boundaries in spherical geometry mantle convection models are distinct in structure, and the position of divergent boundaries shows no clear correlation with the location of active upwellings. Thanks for listening.
Great, thank you very much. Very cool results, Julian. So we do have a few minutes for questions, and I see that there are two in the Q&A box. So first, Sean Trim is asking, Was the Rayleigh number defined as a volume average or at a specific depth?
The Rayleigh, well, what we've done is we haven't focused so much here on the Rayleigh number. That's one of the reasons I didn't give it, Sean. The Rayleigh number is defined as 1 × 10⁹. But of course, what that really means is that the absolute lowest viscosity, that corresponding to the viscosity at the core mantle boundary, is 1 × 10⁹. The viscosity at the surface is, as I mentioned, 3.2 million times greater than that. So the Rayleigh number there is 10⁹ over 3.2 million. I have not calculated a effective Rayleigh number, which I think Sean might be getting at here. So what I can tell you though is that the thermal boundary layer thickness at the surface is of order sort of between 100 and 150 kilometers.
Okay, thank you. We have one more question. This one's from Sam Butler. Have you calculated topography? Are there features analogous to fracture zones?
That's a great question. No, we haven't yet figured out or haven't gone as far as calculating the topography. That's definitely something I'd like to try and do in the future. The fracture zones may exist. I haven't really gone into looking for those yet. This is really new stuff. So, this is sort of over the past 2 months while we sort of had nowhere to go. We've been sort of putting this together. And actually, for what it's worth, what we've been trying to focus on, in fact, is putting a dense component into these models to model the LLSVPs to see what the feedback might be between a dense component on the core mantle boundary and the plate-like behavior that we're getting. Just because a lot of the current models that include LLSVPs don't model plates. And we're trying to see how compatible or what the two might be together and what feedback may exist between what's going on at the core mantle boundary and what's going on in the lithosphere.
Okay, thank you. There is one more question from Sam that has appeared, but I think we're actually going to have to move on. So perhaps Julian, I think there's a way that you can type the answer to that question.
Okay.
If you can see that.
The box.
Then I think, yes, yeah, and then I think it'll be visible to others. Okay, and actually Sam's last question about topography is a really nice segue into our next talk, which is by Jolante van Wijk from New Mexico Tech. And she's going to be talking about dynamic topography in the ocean basins. Okay, thank you, Jolante.
All right, thanks. So I'm gonna try to share my screen and then show you my PowerPoint. Right, can you see my PowerPoint?
Yes.
Great. Okay, so together with Nick Ellis, who started this work as a master's student at New Mexico Tech and who is now a PhD student in paleoclimatology at University of Michigan, we constrained dynamic topography of the Somali Basin as associated with the Afar mantle plume. And this is approximately in the study area that you see on this very nice NASA image towards the right. So this map shows our study area. So we're focusing on the Western Indian Ocean and specifically on the Somali Basin. Also indicated on the map, you can see the Afar plume of impingement, the area of impingement in the red circle. So in this talk, I will show you how we reconstructed dynamic topography that is associated with the Afar mantle plume. And for this, we use the marine stratigraphic record. And by constructing this dynamic topography, we were able to estimate when the Afar plume arrived. What we found is that there was about 650 meters of dynamic topography in the Somali Basin associated with the Afar mantle plume. And this started around 25 million years ago, which marks the arrival of the Afar plume. Okay, a little bit more about this study area. So the Somali Basin formed after rifting and continental breakup, after which Madagascar moved in a southward direction. So that makes the Somali margin a rifted continental margin. Continental breakup occurred around 165 million years ago, and seafloor spreading in the Somali Basin ended by about 120 million years ago. So this means that the Somali Basin has been tectonically quiet for a very long time, and that is an important boundary condition for our method of constraining dynamic topography from the marine stratigraphic record. This red box here indicates the map that you will see on the next slide. So this is our study area. So here towards the left, you can see the same map. And the pink line on this map outlines the Afar plume influence zone as was calculated by Ebinger and Sleep. What you see also on this map in the green circles are DSDP wells that are located within this Afar plume influence zone. And in orange, you can see DSDP and ODP wells that are located outside of this Afar plume influence zone. Well, the wells that are located within the Afar plume influence zone show a very interesting stratigraphic pattern, and you can see that here towards the right. So what you see in the strat column towards the right is the following. I've indicated with the green arrow an Eocene Oligocene unconformity. And this unconformity marks a remarkable change in the stratigraphy here. Below the unconformity, we see a lithology that is characterized by no calcareous deposition. And above the unconformity, we see a lithology that is characterized by strata rich in calcareous nanofossils. On the map towards the left, you can also see in the orange lines and the white line the locations of seismic reflection data associated with a legacy to the seismic survey from Coffin and Rabinowitz. And one of the lines, the one that is indicated in white on the map, is shown here below. I've indicated on this line in the green color this Oligocene Eocene hiatus. And this is a hiatus that we can trace as a reflector throughout most of this legacy to the seismic reflection series. So this is a hiatus that corresponds to this transition from non-calcareous deposition below the hiatus to calcareous deposition above the hiatus. So it is this stratigraphic information that we used to constrain dynamic topography of the Somali Basin. So what is dynamic topography? Dynamic topography is uplift or subsidence of Earth's surface as a result of mantle flow. So upward mantle flow may result in dynamic uplift of the surface. Downgoing mantle flow may result in dynamic subsidence of Earth's surface. The figure that you see here towards the right shows seismic wave velocities in the mantle below Africa. And Africa here is indicated, the coastline is outlined in white. I hope you can see it. So what you see underneath Africa is this large orange blob, which indicates lower seismic wave velocities. Many studies suggest that these low seismic wave velocities here indicate buoyant, so upwelling mantle. And if that is the case, that would result in dynamic uplift of Eastern Africa. Such dynamic topography is always long wavelength, small amplitude. And with long wavelength, I mean hundreds of kilometers to a few thousands of kilometers. And small amplitude would be something like a kilometer or so or less over that entire distance. As a result of that, this dynamic topography being long wavelength, small amplitude, dynamic uplift of Earth's surface would not normally move the ocean floor above the water level. However, dynamic topography of the ocean basins may uplift the seafloor above the carbonate compensation depth. What is the carbonate compensation depth, or CCD? The carbonate compensation depth in the ocean basins is defined as the depth at which the supply of carbonate that sinks from the phodic zone is approximately balanced by dissolution, such that carbonate accumulation rates approach zero. So what that means, I've illustrated here in this figure towards the right. What you see here is schematically indicated the seafloor and the location of the CCD. If the ocean floor is below the carbonate compensation depth, we would have deposition of non-calcareous sediments. If the seafloor, however, is above the CCD, we would have deposition of calcareous sediments. And this change we would be able to see in a stratigraphic record, which is what we use to calculate dynamic uplift of the seafloor. So this is our workflow. We start out with reconstructing paleo water depths at all the 8 well locations of the Western Indian Oceans. We also reconstruct paleocarbonate compensation depths of that study area. And by comparing these curves with each other and comparing them with the stratigraphic records described in these wells, we are able to identify the dynamic swell associated with the Afar mantle plume. So we start out with reconstructing the paleo water depths. Components of our paleo water depth reconstruction are indicated on this figure. Towards the right, you can see schematically a mid-ocean spreading ridge. And as oceanic crust is created there, it is hot, and after some time, and it moves away from the spreading ridge, it cools down and contracts. This thermal contraction results in thermal subsidence that we have indicated and included in our calculations. As the oceanic crust ages, sediments are being deposited on top of it, and the sediment load itself isostatically moves the oceanic crust down. However, the sediment column itself moves the ocean floor up. So these are 2 components that we have included as well. So this is one result of our paleobathymetry calculations of the 8 wells in the Western Indian Ocean. All the wells show patterns like this, in which you can see that most of the time, the ocean floor was actually at a depth of 4 kilometers or more below the water surface. And again, such a large depth, such a deep ocean floor is not going to be moved above the water table, but it can be moved above the carbonate compensation depth. Our next step is reconstructing the carbonate compensation depth of the Western Indian Ocean over time. And we do that as follows. This graph again shows a typical theoretical ocean crust subsidence curve. And as the oceanic crust is above the carbonate compensation depth, we would have deposition of calcareous deposition in our well. And when the oceanic crust dives below the CCD, we would have deposition of non-calcareous sediments in our well. A dynamic swell, as associated, for example, with the Afar mantle plume, might temporarily move our seafloor above the CCD, and that would change. This would show up as a change in deposition in our well from non-calcareous deposition to calcareous deposition, and maybe if the dynamic swell diffuses back again to non-calcareous deposition. There's one complication, however, and that is that this carbonate compensation depth in the ocean basins varies from place to place in the ocean basins quite strongly, but it also varies over geologic time. And that is shown in this figure here. So naturally, the CCD varies from place to place and over geologic time. So we get these changes in our wells from non-calcareous to non-calcareous deposition over and over again. So to correct for this effect, we had to calculate the paleo CCD of our study area, so the Western Indian Ocean or the Somali Basin. Previously, the paleo CCD of the entire Indian Ocean had been calculated, and it had been calculated in 2 studies, one by Van Andel in 1975 and one by Peterson in 1992. We found that since the Indian Ocean is so large, that the chemistry of the Somali Basin or the Western Indian Ocean may not be representative of that entire Indian Ocean. So we decided to calculate our own paleo CCD that you can see here in this purple line. So now we have all the ingredients available to do our dynamic swell reconstruction. So up to the results. I will first show you the results of the 4 wells that are outside of the Afar plume influence, indicated here with the yellow squares. What do they show? They all show the following. They all show that the seafloor was not uplifted here above the paleo CCD at any point in time. So in other words, there was no apparent CCD excursion. Now I'm going to show you the results of the 4 wells within the Afar plume influence zone. And they're indicated here with the green circles. And now we found the following. I'm showing here results of 2 wells, the SDP 241 and DSTP 234. And you can see on this figure these typical ocean bathymetry evolution curves. Now, what we find here was the following. We find that both of these wells, in these locations, the seafloor was lifted above the CCD in the past, and that resulted into calcareous deposition. Now, by comparing the difference between these curves and also the times when these curves cross each other, we were able to calculate a minimum amount of dynamic uplift and constrain this as 650 meters. And we were also able to calculate the arrival time of the plume, which was 25 million years. So to conclude, the Somali Basin wells within the Afar plume's influence record a local depression of the CCD, which we interpret as a dynamic uplift of the ocean floor of about 650 meters. And this is 1,200 kilometers away from the Afar plume impingement center. And this started about 25 million years ago, so that means that the Afar plume probably impinged upon the base of the lithosphere of Eastern Africa around this time, or maybe a few million years earlier. Now, we're currently using this method to constrain dynamic topography of the ocean basins globally, and we're focusing here also on mantle plume locations. And this is all that I had for you today.
Great, wonderful talk. Thank you very much. We've got a few minutes for questions. So please add your questions to the Q&A box. I guess one general question that I have, you focused on one part of the world. I was wondering, are similar characteristics observed elsewhere, and could you apply this method elsewhere?
Yes, absolutely. So we've started looking at all other hotspot and mantle plume locations worldwide, and we see such crossings at several of these hotspots. So by being able to constrain the timing and amplitude of dynamic topography of the ocean basins, that might tell us a lot about mantle viscosity or, for example, plume fluxes. I see one question.
Yes, Sam Butler asks, can you compare the degree of uplift to an amount of buoyancy in the plume?
Yeah, that's an excellent question. That's exactly what we're doing. So the flux of the plume, the buoyancy flux, for example, is dependent or is directly related to the amount of dynamic uplift. So that's excellent. Next question is also excellent. How do fluctuating sea levels figure into your analysis? So we have actually calculated these bathymetric curves with sea level fluctuations. And one of the curves that I showed you had those, you know, how do you say it, included in it. So it doesn't matter much. So it may move the timing 100,000 years back and forth, but that's about it. So it doesn't affect it more than that. So it's a horizontal time scale change if we include them. But that's an excellent question. So we've actually looked at that. Thanks.
Okay, great.
Thanks so much.
Are there any other burning questions? We'll give it a couple of minutes or a couple seconds and see if we've got any other questions that come in.
Thank you.
Okay. Okay, if anyone does have any questions, you can post them in the Q&A box, and I'm sure Jolante will be happy to answer them. Okay, so we have got one more talk left in this session. So this is by Behnam. So Behnam, are you still with us? Yeah, there we go. And he's going to be presenting another kind of global scale study looking at the Chandler wobble and how that relates to the dynamics in the Earth's core. So Behnam, I think you've started sharing your screen, okay, and we can see that. Okay, so go ahead. Thank you very much.
Okay. All right. Okay, I'm a core dynamicist, so you will see a lot of equations here. We didn't see that many today. So first, I would like to acknowledge my colleague, my collaborator, Eve. Let me see if I can start this going. Yeah, the abstract is there. This is the outline. We start with a relatively realistic Earth. I explained how the dynamics of a relatively realistic Earth model is dealt with, and then after that, justification for what we have done. So this is these are the equations for the dynamics of a realistic Earth model. You can see that the displacement is represented as spheroidal and toroidal vector fields, and then these are expanded as such, and then of course solved for. Ideally, of course, we want n to be as large as possible to ensure convergence. Now, for this model, the liquid core is assumed to be compressible, small compressibility, and stratified. And and also the motion is assumed to be near solid body rotation. So U is very small. But the thing is that up to now, only n equals 3. So only 3 terms in the expansion or 4 terms are considered, not that many. So we want to know if the results using this severe truncation are converged. The only way to do that is to increase n, of course, to see if the results change. So what we did was we started with it's difficult to do it with the with the realistic Earth model. As you saw, the equations are very complicated. So we started with a simple Earth model with a homogeneous liquid core and rigid inner core and mantle. And we saw that for this model, for the very simple model, the frequencies of Chandler wobble, tilt-over mode, free core nutation, and inner core wobble, they converge very rapidly. So 4 or 5 terms were enough for the convergence of those, except for free inner core nutation. So we decided this is the free core nutation. This is from a paper from 2017. You can see that as you increase, this is where previously they had been, the solutions were truncated at this, in this area, 3 or 4, and I think one person included 5 terms. And you can see that we included all the way to 40 terms. The frequency, the period of free inner core nutation never converged. It just gets closer and closer to this average value, but it never converges. So we decided to have a look at the eigenfunctions to see why that is. So in this case, we started with the inner core and the mantle wobbling at different rates. And the inner core, the fluid core is still considered to be incompressible and homogeneous, and liquid mantle and inner core were rigid. And you can see that the reference frame actually rotates at this frequency. It's rotating uniformly. Omega k is k equals to 1 is associated to the inner core. K equals to 3 is associated to mantle. And this is the alpha is the amplitude of wobble. So if we did that, then in the liquid core we have the Poincaré equation describing the dynamics of the core. Here we defined sigma, which is equal to the amplitude, the frequency of the wobble divided by twice the frequency of rotation. and chi is the reduced pressure here. If we define it this way, then U, the displacement in the core, is defined as such. And if there is no wobble, if we only consider uniform rotation, then n dot U is equal to 0. This is Poincaré problem. These two together is known as Poincaré problem, which is actually core dynamicist. It's in core dynamics. This is actually an ill-posed problem. Ill-posed in a sense that this equation is an initial value problem, but it is subjected to boundary conditions. And only toroidal modes survive if we consider this situation, n dot U is equal to 0. So that means, of course, we are considering rotation. We want to show that that's not true for the core modes, for not core modes, but wobble modes, which are, of course, also core modes as well. So what we did was we looked at a special case. We attached inner core to mantle, so the two of them rotate at the same rate. They don't rotate independently. This is actually a good approximation, I believe, because I mean, if you consider that if all of them rotate at uniform rotation, then this is even more realistic model that we let the two mantle and inner core actually wobble at the same rate. And so you can see that now we have the same problem, except that the boundary condition becomes n dot U is equal to omega m cross R. So if we, and of course, we already defined m to be like so. If we apply the boundary conditions, now chi, the pressure, has a particular solution. We use this solution, and then we use the boundary condition, knowing that n is defined as such, the normal to the boundary is defined as such, we get a solution for the boundary condition. And as you can see, we have two unknowns here. One of them is C, which is from chi, and the other one is alpha, of course, which is the amplitude of bubble. If alpha is equal to 0, then of course you can see that here we have one solution, and that solution is actually the frequency of the spin-over mode, which is a purely toroidal mode if alpha is equal to 0. So that means if we have rotation, we have uniform rotation. So we need another equation, and for that we use the conservation of angular momentum. You can see that I'm not going to go in detail. These are the changes in the angular momentum here, and in the liquid core we have this. You can see that A here, E is defined as the moment of inertia about a polar axis minus moment of inertia about A is moment of inertia about an equatorial axis divided by A. That's the dynamical ellipticity. And if we put all of these together, well, because mantle and inner core actually rotate at the same rate, we can put these two together and define, I named them angular momentum of mantle and inner core for both about an equatorial axis and polar axis, and then I defined the E prime to be the dynamical ellipticity if we put both of them together. And if we do that, then the angular momentum conservation equation becomes like so, and you can see that you have alpha and C in this equation. We put these together in a algebraic equation, and for solutions, then the determinant of this equation has to vanish, and that's what we get for the determinant. And if we solve for that, you can see that we get a solution for free coordination and for Chandler wobble of the body. So what it says here is that the ill-posedness of the problem does not affect the ill-posedness does not affect the presence of especially Chandler wobble. Now we can argue that, okay, free coordination is a toroidal mode and therefore it should be there, but you can see that the Chandler wobble is there as well. Now, you can see that Chandler wobble, the frequency of it is first order in electricity. So if you substitute here, first order electricity, this sigma is squared, so this term becomes very small. And therefore, we have a geostrophic for Chandler wobble, we have a geostrophic equation, and we expect that we will have Taylor columns during the excitation of Chandler wobble. This is free coordination. You can see that it is indeed a very toroidal mode, but this is the free inner core mutation. These results are actually from a more realistic Earth model. We have allowed the inner core also to wobble to calculate these. And so we were able to calculate also the free inner core mutation. Free inner, you can see that even though the fluid is inviscid, we can very clearly see the characteristic lines. And the characteristic lines, the characteristic surfaces are intercepted by the inner core, and we believe that that's why the convergence is very slow. You can see that I showed this before. I'm showing it again. You can see that if you calculate the free inner core mutation, the convergence is very slow, or it doesn't converge. I mean, we don't know if it converges or not. All we know is that it gets very close to the average. This is actually a picture I just wanted to throw it in. My students took in my lab. The frequency here is near zero. You can see the Taylor columns, which are actually associated with the free Chandler wobble because it's a geostrophic mode. So you should be able to see the Taylor columns. These are for Chandler wobble again, when inner core is included. You can see that the Taylor column, these are computed, of course. You can see the Taylor columns very clearly. And that's all I have to say. The reason, of course, we decided to look at this is because we submitted a paper and it was opposed by a core dynamicist on the ground that Chandler wobble would not be excited in a shell because the core was inviscid, and therefore the equation is ill-posed, and therefore there would be no, unless if you include if you include viscosity. This is inviscid, and you can see that the Taylor columns are very clearly visible, and the eigenfunctions are actually very regular. Okay, so that's all I have to say today. Thank you.
Thank you, Behnam. That was wonderful. So I see that there's a question in the Q&A box. Okay, so Phil McCausland is asking, what is the amount and the time period of inner core nutation?
Inner core nutation, well, this is not a realistic Earth model. The period of it for this model is about 915 days, something close to that. But in a realistic actually maybe 745, I think 740 or so. That's the inner core wobble that is 950. But for the realistic Earth models, it's somewhere between 3 years to 7 years. It differs on what, that's actually one of the reasons we have decided to study these and study them in more details, because there is so much discrepancies between the calculated results. It's somewhere between, I don't know, 3 years to 7 years for more realistic Earth models.
Okay, thank you. So I got a direct message to me from Julian, who is asking, are there any estimates of the range of viscosities in the outer core from the maximum to the minimum viscosity?
Well, I know that it's very small. I think it's of the order of 10 to the power minus 15 or 14 or so. So it's just very small, but offhand I don't remember.
Okay. So question from Ian Lum. Any comment on the excitation of this wobble? Is it possible that motions in the core play a role?
Which wobble? Is it free inner core nutation or? I mean, if it is
not
free inner
sure.
core, okay, if it is free core nutation and free inner core nutation are both associated with the fluid core. So if there is no fluid core, there is no free core nutation and free inner core nutation. But Chandler wobble and inner core wobble are they are affected, their frequency and period are affected by the presence of the liquid core. But if there is no liquid core, they would be excited.
Okay. And so does that apply to the Chandler wobble? That was specifically
Yes,
what he was asking about.
that's right.
Okay.
Okay, Chandler wobble, yes. Chandler wobble is that Eulerian wobble of the rigid body, but then it's modified by the presence of the fluid core. Yes.
Okay. Great. So I'm not...
Say hello to Ian. We know each other from York University.
Okay, great. I'm not seeing any more questions, and I think we're right at the time that we should be wrapping up. So thank you, Behnam, and thank you to our other 4 speakers for a nice range of talks on all different topics. So I would also like to thank 2 people, Daryl Kwong and Didar Ibrahim, who are, Daryl is coordinating this talk series this summer, and Didar has been helping with the technological aspects. So thank you very much to both of them for all of their work. And just a couple of general announcements. Next Friday, there is nothing scheduled for the talks. So we'll have a break from the talks for 1 week, and then on July 17th, there will be talks in the hydrology section, which everyone is welcome to attend. And then the following week, July 24th, we'll be back for Solid Earth section talks. We've got, I think, another 5 talks lined up. And then in August, we are also considering having the Solid Earth AGM meeting on August the 14th. So stay tuned for an announcement about that. So with that, I think we'll end the session. So thank you all for attending. And again, thank you to all of the speakers for their wonderful presentations. Okay, and so I hope to see you again in another couple of weeks. Okay, goodbye, everyone.